Have you ever wondered why your flashlight uses more than one battery? Or how your phone battery is powerful enough to run complex apps? Well, it all begins with a simple concept. A single cell can only provide a limited amount of electrical energy, both in terms of voltage and current. When we need more power, we connect multiple cells together. These cells can be arranged in two different ways, either in series or in parallel. When cells are connected in series, their voltages add up. This is ideal when a device requires more voltage. When cells are connected in parallel, they share the load. This means more current is available and the total internal resistance is reduced. Visual cue: show two configurations, one with 3 cells connected in series and the other with 3 cells connected in parallel. For example, to create a 12-volt battery, we can connect 8 cells in series, each providing 1.5 volts. That is, 8 multiplied by 1.5 equals 12 volts. Let's now look at what happens when cells are connected in series. In a series arrangement, the positive terminal of one cell is connected to the negative terminal of the next. All the cells are aligned in the same direction. In this setup, the total electromotive force, also called total EMF, is equal to the sum of the individual EMF values. We write this as epsilon total equals epsilon 1 plus epsilon 2 plus epsilon 3 and so on. That is, epsilon total is equal to epsilon 1 plus epsilon 2 plus epsilon 3. Similarly, the total internal resistance is the sum of the internal resistances of all cells. Our total equals R1 plus R2 plus R3. The current flowing through all cells in series is the same because there's only one path for the charges to move. Visual cue: show a circuit diagram with 3 cells in series, total EMF, total resistance, and a single current passing through an external resistor. Now, let's consider what happens when cells are connected in parallel. In this arrangement, all positive terminals are connected together and all negative terminals are connected together. In a parallel connection, assuming all the cells are identical, the total EMF remains the same as that of a single cell. So we write epsilon total equals epsilon, or simply epsilon total equals epsilon, but here's the benefit: the internal resistance decreases. If we connect n identical cells and each has an internal resistance of R, then the total internal resistance becomes R total equals R divided by n. So we say R total equals R over n. This means the current divides among the cells and each cell handles less current, reducing load and heat. Visual cue: parallel circuit diagram showing current splitting into multiple branches connected to the same external resistor. So, parallel connections are useful when you want to supply more current while keeping the voltage the same.
Let's now compare series and parallel connections side by side. In a series connection, the total EMF increases, but internal resistance also increases, and the same current flows through each cell. In a parallel connection, the EMF remains unchanged, but the total internal resistance decreases, and current divides among the cells. As a result, series connections are better for high voltage needs, like in inverters or emergency lights. And parallel connections are better when high current is needed, such as in electric vehicles or audio systems. In fact, laptop batteries and power tools often use a combination of both series and parallel arrangements for efficient power delivery.
Let's apply our understanding to a solved numerical example. Given, we have 3 identical cells. Each cell has an EMF of 2 volts and an internal resistance of 1 ohm. They are connected to an external resistor of 3 ohms. Let's find the current in 2 cases. Case 1, series connection. Case 2, parallel connection. First, for the series case, total EMF is equal to 2 plus 2 plus 2 is equal to 6 volts. Total internal resistance is equal to 1 plus 1 plus 1 is equal to 3 ohms. Total resistance is equal to 3 plus 3 is equal to 6 ohms. So, current I is equal to 6 volts divided by 6 ohms is equal to 1 ampere. Now for the parallel case. Total EMF is equal to 2 volts. Total internal resistance is equal to 1 ohm divided by 3 is equal to 0.33 ohms. Total resistance is equal to 0.33 plus 3 is equal to 3.33 ohms. So, current I is equal to 2 volts divided by 3.33 ohms is equal to approximately 0.6 amperes. Conclusion. In this case, the series connection delivers more current. But remember, the internal resistance is also higher. So, the best choice depends on whether your system needs more voltage or more current. Let's revise what we've learned. In a series connection, total EMF equals epsilon 1 plus epsilon 2 plus epsilon 3. Total internal resistance equals R1 plus R2 plus R3. Current is the same in all cells. In a parallel connection, total EMF equals epsilon. Total resistance equals R divided by N. Current splits across the cells. Use series when you need higher voltage. Use parallel when you want more current and less internal resistance. So, whether it's powering a remote or driving an electric vehicle, the way cells are combined affects how much energy is delivered, how fast, and how efficiently. I hope you now have a clear understanding of how cells work together in series and in parallel. See you in the next session with another fascinating concept from physics.